Hello, everyone, and welcome to this latest Zero Defect Zero Waste webinar series. We're going to wait for a couple of minutes so we can give some time for people to join, and we'll be starting right back. So I think we can start now, Christian. So everyone, once again, good afternoon and welcome to this latest webinar from the Zero Defect Zero Waste series. Today we're featuring Dr. Christian Eike from AIMEN, and he's going to present us the webinar for artificial intelligence supported monitoring system for defect detection in submerged arc welding. So, Christian, whenever you want, the floor is yours.
Okay, thank you very much for the introduction. So, as mentioned, I'm going to talk to you today in this ZDZW project webinar about AI-supported monitoring system for defect detection in submerged arc welding. We will travel into artificial intelligence concepts, and in my opinion, that's a fascinating topic. I hope you will enjoy it as much as I do. Okay, then first let me introduce myself. So I have a PhD in physics for the University of Leipzig in Germany. And currently I'm a senior scientific researcher at AIMEN Technology Center. And as expertise, I have skills in artificial intelligence and data analytics in materials science, data acquisition and processing, samples preparation from nano, micro to macro scale, and advanced sample characterizations like using cryogenic systems, FIBSEM, ICP, reactive ion etching, squid, atomic force microscopy, sputtering, and have also experience with DC and pulsed magnetic fields. And since 2020, I'm working at AIMEN at the forefront of AI-driven scientific innovation. So here is the outline of this talk of today, and I will introduce you a bit about the project itself, then an introduction to artificial intelligence. And in my opinion, this is an important point since artificial intelligence sometimes is seen as a black box. So here you can have an introduction overview of how it works. Then we will go through overview of the monitoring systems we use in submerged arc welding. And then we will go through the defects in the welding process. Then the defect detection using electric signals and using also computer vision. And finally, we will approach with the conclusions. Okay, now a general review of the ZDZW project, and the aim of this project is to develop digital non-destructive inspection services as a set of strategic technologies to improve production efficiency, zero defect, and sustainable manufacturing of European industries. So this project had received 11 million from the European budget. It has 3 years of duration, and we have 27 partners from 10 different countries. Okay, so going a bit more in details. Would you like to reduce waste and defects in your manufacturing process? I think everyone would like to do it, right? And here, explore the benefits of this project because it can offer you, and you can learn more about it to improve your manufacturing process. If you see this QR code here, you can point your mobile on it, and this will direct you to a video about the project, and you can have a better idea of what is being done in this project. Okay, so here you may have free testing, and you may improve your productive by 7%, and decrease in the energy consumption of 25%, and reduction of material waste by 50%. Please take a look at it, and yeah, we are open to answer you. So what inspection solutions will you have at your disposal? So here you will have a volumetric inspector. This is to work in the production line, capturing images in real time without requiring reconfiguration. Then a surface anomaly detector with a 3D camera and artificial intelligence algorithms to ensure the quality on the production and identify visual defects. Then you have also the mechanical hardness inspector. That's a real-time inspection based on digital twin to define the microstructural and hardness evolution during induction heat treatments. Also, you have base integrity assessment with acoustic emissions. This is to assess the predictions in an early stage of the quality of the product and anticipates possible defects arising during the manufacturing process. And welding process monitoring. And here you have an online welding defect detector, which allows to estimate the presence of defects during the welding with artificial intelligence analysis. Okay, then let's start here with the introduction to artificial intelligence. Here I will prepare you to understand a bit more about this topic before we get into the applications with the defect detections using artificial intelligence. Okay. So here, the idea of artificial intelligence became popular by this guy here, Alan Turing, with his famous question, can machines think? In his publication that you can see here of 1950, entitled Computing Machinery and Intelligence. And here in this article, Turing described a machine capable of tricking a human and pretending that he was also a human. And this became to know as the Turing test. Okay. So here we can follow a timeline of events. Artificial intelligence was not invented by one person, but it was a collection of continuous contributions of many different persons. So we can start already here in 1642 when first mechanical calculating machine was built by this French mathematician. I think everyone heard about him, Blaise Pascal. Then we can follow this timeline to see how we came to this stage we are today. Everything today you hear has some sort of artificial intelligence, a product, or everything you buy today, it has artificial intelligence somehow in it. So here we see the Alan Turing paper in 1950. 5 years later, the artificial intelligence coined during a conference only devoted for this topic. Then the first natural language program, ELIZA, came in 1965 with a similar concept that we see today in the chatbots. And we can follow this timeline until we got, for example, here in 2002, the iRobots that can clean your house. And going further, in 2011 until 2014, we got this personal assistants that we can have at home, like Siri, Google now Cortana, to use speech recognition. If you have an Alexa at home also, this is artificial intelligence. Here in 2014, we came with very innovative artificial intelligence method, the generative adversarial networks. This is used here in many different fields to make pictures of people that does not exist, that they don't exist, or even like big companies are doing movies, and for example, Pixar, that is this animated movies, to render in high quality. They are using this kind of technology. And since 2018, we can say that most of universities have courses in artificial intelligence. So now you can even do that at the university. So, and what is artificial intelligence? So that's my question to you. So it depends who you ask. If you go to Wikipedia, you will find that artificial intelligence is the intelligence of machines or software as opposed to the intelligence of living beings, primarily humans. It is a field of study in computer science that develops and studies intelligent machines. If you go to the Stanford course, you will find artificial intelligence is the science of making computers work without being explicitly programmed. But if you ask me, I will tell you that artificial intelligence is a branch of computer science that deals with making computers behave in a way that mimics human intelligence and allows them to solve problems that require thinking. So we can summarize it as any attempt by a machine to imitate the human intelligence. If a human does some action that we can say, look, that's an intelligent action, and a machine can imitate this action and make a decision like a human, then that's an artificial intelligence. That is, the machine executing something that a human would have to have intelligence to do. But obviously, this is very generic. How many different intelligent things a human is able to do in thoughts, actions, and so on? The machines cannot reproduce everything. In some specific areas, the machines are performing better than humans, but in many other areas, the humans are ahead the machines. So the definition of artificial intelligence over the time. This has been changing over the time. If we think of years ago, in a time when there were no calculators and computers, solving a calculus integral could be a very complicated task. So you should have knowledge of mathematics and calculus. It was not a task that anyone could do, and one should have some intelligence to do it. Then calculators that could solve these integrals much faster than humans appeared. And nowadays, it's no longer considered that doing a calculation is an intelligent action. We consider that a calculation done by a calculator or a computer or opening some website on the internet that makes calculations gives us the impression that there is a code executing a command. It's like a reproduction of an algorithm that gives a result. And nowadays, I believe that few people would consider a calculator as an artificial intelligence. But in the time these calculators appeared, the people could think, look, and just humans were able to do these calculations. Now, a machine is also able to do it. This is an artificial intelligence. And as time goes by, we get used to it and things become more banal. And then we start to consider that it's no longer intelligence. And that's the reason the definition of artificial intelligence may change over time as technology evolves. So, for most people, artificial intelligence is probably the most mysterious kind of information technology. Here we have some examples of artificial intelligence that we use in everyday, like movie recommendation on streaming platforms, and speech recognition like Alexa or Siri, image recognition, some virtual assistants that we communicate with them and they give us answers, self-driving cars, and verification of purchases with a credit card to find out if any purchase had anomalous behavior. So I could stay here all day citing the applications of artificial intelligence in our daily lives. But nowadays, almost every electronic device uses some sort of artificial intelligence. But all this we can consider to be in specific domains. So, for example, an artificial intelligence that plays chess is very good on doing that, but it cannot do other things. And also an artificial intelligence for speech recognition is very good on it, but cannot do a different thing. So for this reason, artificial intelligence is still very restricted to a specific field of activity. And there is a terminology for this called narrow artificial intelligence, which are expert systems at doing something specific, different from the humans that can do well many different things. And there is a more general area of knowledge called artificial general intelligence, AGI. This concept arose in an attempt to create a true artificial intelligence, similar to a human mind, to learn anything in different fields of activity like a human. And there is research in this area trying to develop this kind of artificial intelligence. If you look at the X description of the CEO of DeepMind, which is one of the largest artificial intelligence companies in the world and belongs to Google, we can see that he's working on building AGIs. This is one of the main lines of research in this and other companies. And that's a branch that is growing significantly, and the tendency is to have more general applications. So if we want to imitate human intelligence, how about starting with the human intelligence? We humans learn from the moment we are born and begin to observe and interact with the environment around us. Everything that our senses, pay attention, senses, capture from the moment we are born is transformed into data for our brain, and in this way we manage to adapt to the world. An interesting thing is that we learn to observe patterns. See this image here. We can recognize shapes, we can recognize colors, we can recognize rotations. So we recognize patterns. But let's imagine a scenario where a child in the learning phase is holding a feather and then a pencil, and the child lets them fall to the floor. The child will think, interesting. The child then repeats this experiment many times with the feather and the pencil and other things and getting the same result. Then he will think, more interesting. And the child concludes that whatever he lets go of his hand will fall to the floor. This is interesting because a child does not need to know about gravitational force or solve physics equation to understand that everything he lifts and let go will fall to the ground, nor that he is on a planet where the gravitational force attracts everything to its center. To understand what is happening, the child just needs to do a series of experiments and observe that there is a pattern in these experiments. In other words, the child learns to observe and analyze patterns. All these experiments turn into data obtained by the child's brain, and it will be used for the rest of his life. So this is a very important concept to understand the artificial intelligence. So then this example was just one of the countless observations and interactions of the environment that we have since the moment we were born until today, like from being able to differentiate a dog from a cat, reading traffic light, reading and learning traffic signs and driving. And we always observe and interact with the environment and thus obtain data that help us to carry out tasks in our daily life. If we want to get artificial intelligence, then wouldn't it be a good idea to get a method that mimics the way the human learn? I mean, a method that makes the machine obtain data from the world, observe this data, and then be able to perform tasks. And that's exactly the idea of machine learning. So, machine learning is a part of artificial intelligence research, which seeks to provide knowledge to computers through data, observations, and interactions with the world. This acquired knowledge allows the computers to correctly generalize to new configurations. This was said by Joshua Bengio. He won the Turing Award in 2018. But what does this definition mean? So we do not explicitly say the machine how to interact with the data. The model should learn by itself to understand the relationship between the data. And how to teach a machine to distinguish, for example, dog breeds. Okay, so we can think that machine learning is a method that makes the machine receive data, observe, interact with this data, and we will let the model learn by itself, and the machine will have to find by itself to understand the relationship between the data. And any resemble to real life is not mere coincidence. So imagine that you want this machine to distinguish these dog breeds. You as a human know that what a Labrador is, but for that you needed to have seen pictures or the animal itself. And the same happened for other dog breeds. Otherwise, you wouldn't be able to tell the difference between a Labrador and a Pinscher. And this distinction is extremely important, as one you can pet and the other can bite you. Now, you are an expert in distinguishing dog breeds, but you want to teach a machine the same thing. And how to do that? How can we teach the machine? So initially, you will need a data that can be photos. For example, you have here photos of different dog breeds. You feed these photos to a model, and this model alone, just looking at the photos, will have to learn how to differentiate one breed from another. There are many different ways to do this. And many is split in two branches, known as supervised models, which is supervised learning, and unsupervised methods with the unsupervised learning. And the difference here is in the kind of data we have, if they're labeled or not labeled. So now that you are familiar with the idea of artificial intelligence, we can start getting a bit more deep in the concepts. And here we can summarize that artificial intelligence are theories and techniques that aim to artificially simulate intelligence. And the bounds are not clear. You can see here in this image like a cloud form shape to identify this artificial intelligence with no bounds. Then inside it, we have the machine learning, which are statistical approaches that aim to make algorithms able to learn from data. That means to adapt a model to answer to an objective according to the data. And inside the machine learning, we have the deep learning. And deep learning are machine learning methods based on the use of the so-called deep algorithms. That means on the use of a chain of non-linear transformations. And generally, they are deep neural networks. So now keep always in mind data, objective, and model. These are the three things you have to have in mind when working with artificial intelligence. In machine learning, data, only having data is not enough. They must also possess required features to address the objective. Quantity of data is important, and it depends a lot of the problem you want to solve. And also the quality of the data is important, and the dimensions and the complexity, and to address the function that you don't know at the first moment, you want to approximate. We will talk a bit more about it later. Then we have an objective, usually corresponds to a mathematical function that must be optimized, like error minimization or score maximization. And this is often called as loss function. A classical example is the squared Euclidean distance between a prediction y hat and a true value y. This y hat is what the output that the artificial intelligence model gives you, and the true value is the real value you have to compare with the prediction with the real value. And finally, the model. In the model, it represents a function that predicts the y hat from input data x. And theta are the parameters of the function. So this function depends on the model you have. And in the literature, if you have a look, this is a table, a tree of models in 2013. So you can see already here that there's a lot of models that could be used. If you ever have done linear regression, as you see here, you have worked with machine learning. And nowadays it's impossible to show this because the number of models is so huge you couldn't see here. In this image. This is just to exemplify. So then the choice of models. So first you have data. Is the data labeled? Yes, I have the labels. Then we are going to supervised models. Is the data discrete? Yes. Then we can go through classification models like a support vector machine, neural networks, decision trees. And if you have continuous, then you can go to regression methods. You can use linear regression, Gaussian process, or neural networks. Is the data not labeled? Then you can go to unsupervised methods. If you have discrete output, then you can go to clustering methods. If they are continuous, you can go to embedding models. And if it's kind of labeled the data, you can also go, if the object is modelization, to generative models, or for adaptation to reinforcement learning. Okay, and here the supervised learning, we have the data, X and Y, and X are the features. We will feed the machine learning model to predict Y. So Y is the output we have to train the data. For example, if you have an alloy, you know physical parameters like melting temperature, hardness, and you want to predict some other physical parameter. You add all the information you have here in X, and Y will be what you want to predict. For example, some physical parameter like the stress strain they yield, you can try to predict using the other values you know about this alloy. And you also have a class of models that you can adapt to it. So the model depends on the data you have. And after this, we define an objective function, the loss function. And we find the optimal parameters of theta, which are the parameters of the function of the model we want to use, that minimize this loss function. And if you remember, we can make a comparison between the prediction and the real value, and we want to minimize this difference. Okay, so in summary, we have the input data, then which is a raw data that in the specific domain of physics, chemistry, biology. Then you have to work on this data to feed the machine learning algorithm. Then you use it in the algorithm. The algorithm will learn and will provide an output data. And you can have here a loop to optimize the parameters theta. And you can stay in this loop until you get the best hyperparameters theta. And you have a model to predict with the best precision possible the output data. Then the supervised learning requirements are the data and the format, which could be images, time series, or scalar values. and the loss function in summary. And the unsupervised learning, we have the data and the class of models. So here you see we don't have the Y, which is the prediction. We want to process this data and create clusters of similar data or find connection structures in the data. We define an objective function and we find the optimal parameters that are similar to the supervised learning. So here in summary, we have the input data, then you feed you work on the data to feed the machine learning algorithm, and then you train the model. You have here the model prediction this loop until you get the best hyperparameters, and you can have, for example, a cluster that group data by different clusters. So here also you can have the as database the input data, then we have no expected output data, and the format can be anything, image times series is scalar values, and also the loss function. And here it depends of the objective. If you have clustering, similarity measure between the data, or embedding, like dimensional reduction. Maximal variance of the data in a specific subspace, like this principal component analysis. Okay, then let's go to the overview of welding monitoring system. We have finished with the theory about artificial intelligence, and let's put the hands on the work now. So what do you need for artificial intelligence? What I have been telling you, data. And the quality of data is very important. If you have bad data, you will have bad models for artificial intelligence. So the hardware and software architecture requirements in a welding monitoring system should be adaptable to different automated or semi-automated welding processes and enable synchronization of heterogeneous data sources, and should minimize intervention on existing welding stations, and also should assure real-time processing capabilities. So here is the architecture. You have a digital platform, and we have here a PC, personal computer, where you can have the local data storage and data analysis. And here you have the external connections like USB for digital and analog signals, industrial protocols like Profibus, and oscilloscope for high frequency signals, and also for cameras. And covering a great variety of possible sensors, we can have a current and voltage probes for high frequency signals, thermal information for punctual parameters or infrared cameras. Also, wire speed can be acquired through encoders, and torch position regarding at each time step, industrial protocol or adding encoders. So here we have a lot of sensors to acquire data to feed our models. Then we have to store this data to be able to work with it. And one way to do that is using this format, which is HDF5, which is a hierarchical data format where you can have all your data there. You can, in this kind of format, you can have different kinds of data like images, scalar, vectors, everything is possible. You can have everything organized in this kind of data and data format. And here is an overview of the system that is used for this data acquirement. For example, here in this image, you can see in the green spot the encoders to measure the speed of the wires, and you can have here a camera like in this blue part. This yellow part here is profilometer to see the surface, and you can have like here in the red arrows pyrometers to check the temperatures. Okay. Okay, then let's go to defects in welding process. And defects, they can appear and they can be very different from each process you are welding. So here are some examples of defects that you can find in submerged arc welding, like underfilled. When you have it under the bevel, you want to weld, you have this undercut or poor penetration, so you have here lack of weld, lack of fusion, sputter when you have a lot of parts around the bead, porosity, overlap, inclusions like inclusions, excess reinforcement, and cracks and burnout. So there are many different kinds of defects you can find. So here I put an image of coupon. So you can see here, these are two parts that we want to weld. In the middle, you can see the weld that was performed. And in this case, two kinds of defects were found. The cracks, you can really see here, the spot zone, and the pores. And another example, as you can see here, is incomplete fusion. So this here was not completely weld. Now, what can we do? We can try to detect defects using, for example, the electric signals of the process. And for example, here in this other coupon, we have used this model LSTM, which stands for long short-term memory for detecting porosity. And what we can do, we can have windows here across the weld. We can identify the defects, the pores in this case, and then we can label them. We put 0 where is no defect and 1 in the windows that have defects. Okay. And in this model, we have a movable window that is moving across this length here. So what this model does, you have here, for example, these three first parts. It checks the signals, the electrical signals. And then based on this history, it will try to predict the next step, the future. So you have here the signal and the model reads this. Once the model, of course, is trained and prepared to receive this information. And then it can predict the next part if there will be a label 0 or 1, a defect or not. Okay, so and then it starts from the second square and do the same. Okay, then we have the input size, which are the three first, and then the prediction, which is the last block here. So then looking at this model more deeply, we can have some results, for example, that you can see here, that in this length, we are talking about this length here, okay? The model has predicted here 3 pores. In reality, 1 appeared. Okay, the model worked. It predicted the formation of pores where it should be, but the number was not right, but at least it could predict in the right length piece. And in this other part, it was predicted one pore and it appeared a pore. So the model is based on the behavior of the electrical signal, and with this, it can gives you an answer if there will be a pore or not based on this knowledge of the electrical signals. Here, for example, the model has predicted one pore, but in reality, it didn't appear. So the model is not perfect. Also, the signals they are quite tricky to deal with, and to have a 100% accuracy model is not possible, but at least we could get something near to 80%. So it's already a good hint. So it could say to an operator, okay, here probably will happen some pore. Please have a look, and the operator can check it. So this is very useful for helping operators in detecting defects while using this welding, submerged arc welding process. And here, for example, was observed in this length range one pore, but unfortunately the model didn't predict it. But in the other parts, no pore was predicted and no pore appeared. So this is for you to have an idea how it works. Okay, then here is for you to have an idea. So we have a voltage here, and then we have the input data, which is this red part, and the model here could predict this orange part, but the real data is this gray here. Just to have an idea of how it works. Another thing that we could use for defect detections is like we have a current here, and we can train not a model to identify anomalies in the signal. And this model is called long short-term memory autoencoders. And you can set a threshold to say, okay, any points below this line is an anomaly. So if you have a look at this part here, you can see that this really is an anomaly. And this may generate some defect in the weld. And this can give the operator an alarm that an anomaly happened, and the operator can check if a defect occurred because of this anomaly. It could be that not, but possibly would happen. And using this kind of method here, detections can be done every second. Okay, so let's go to the final part of this presentation, which is the defect detection with computer vision. A brief introduction about computer vision, and we will now start learning a bit about the YOLO algorithm, and YOLO stands for you only look once, because the model passes just one time through the data, and is an algorithm used for object detection. And it's so fast that has become almost a standard way of detecting objects in the field of computer vision. And when we talk about object detection, we are talking about the class the object belongs, the position and the bounding box around the object within the image. For example, you can see here that it's detecting in real time cars and trucks passing. And here in an office, a chair, a book, and scissors, and TV, and so on. And the numbers you see here are the given probability to be this object. So take a look at this image. Let's imagine we have trained a YOLO to detect persons and cups. In this picture, you can find a picture of mine. And here, the YOLO has detected a person, but no cup, because there are none. Let's have a look on how it works. Look at this vector here. Here, PC stands for the probability of a class that is in the picture. That means if there is a person or a cup. This will be 1 if there is a person or a cup, or 0 if none of them are there. Okay, then we have bx and by. These are the coordinates of the center of the image that you can see here in this white point. And bw and bh are the width and the height of this bounding box, which is here with me inside. And we have also C1 and C2, which are the classes. Since there is a person, C1 is 1, but there is no cup, then C2 is 0. Okay. Then we can now train a YOLO to detect pores as well. And what I'm showing you here are only 2 images, but in our training data set, we will have many of them. And using this information, that means the image and the labeled pores, where you can see here in the squares, we can train a neural network, a YOLO, to detect pores using the same way I have explained in this slide before with the picture of myself. So now we have a trained model. And now when you give some type of image or video or real life image, the model can produce the vectors, which basically tell you the bounding box, rectangle around the object in the image. For example, here. So if you put this in the model, you can have this in real time. It will just show you if it's an image or a video, doesn't matter. And following the same structure with the vector that I showed you. In this case, we have just one class, which are the pores, but we could increase it with cracks or other kind of different defects. Okay. And to finish it, I would like to come to the conclusions. And what we have seen here in this webinar, we have seen basics of artificial intelligence, where we can see that artificial intelligence do not have well-defined boundaries. Machine learning and deep learning are a subset of AI. The formation of defects in welding processes with different kind of defects, the monitoring system that we can use to acquire data to provide the necessary data to train AI methods. We have then come to the electrical signals, where we could predict or identify possible defects. And we have seen some concepts of computer vision, showing that we can train this kind of network to identify defects in images or videos or real life videos. So these are just some few examples of the use of artificial intelligence in that we can use in submerged arc welding to improve the manufacturing process by preventing formation of defects and identifying them. So I would like to thank you for the attention, and I'm open to questions.
Yes, thank you very much, Christian, for your webinar. Really, really interesting and very insightful. So as you mentioned, if there is any question from the audience, you can either write them down in the chat, or I can also allow you to speak and make the question up loud. If there's no questions from the audience, I can give you a couple of them. So in the meantime, in case someone from the audience is writing them down in the chat, I have a couple of questions for you, Christian. I hope they're not too hard for you. I'm sure
Sure.
they won't. I'm sure they won't. So when you were training the different models for detection and for the pores and the cracks, what were some of the difficulties and the shortcomings you had to overcome to get to a really accurate model?
Okay, this is a good question. As I have mentioned, the data is very important in artificial intelligence training for models. And the amount of data was a bottleneck for us because as much data you have, better are going to be the models. And if you don't have enough data with a limited number of data, in this case, the electrical signals, for example, you can train the model and reach an accuracy that could be better if you have more data. So the amount of data would be a big factor here because the model analyzes the behavior, the peaks, and then based on this knowledge, it can predict or provide you an insight saying, okay, this might be a defect or not. So the amount of data.
Okay, thank you. Thank you very much for your answer. And then now speaking specifically to the solution and the defects of the weldings, what were the most important defects that you detected and the most difficult ones you detected, and how were you able to detect those tiny little defects that may be harder to analyze?
Yeah, okay. The easiest defects to detect were the pores because they are, for example, well shaped. And then with computer vision, for example, this was very straightforward. And the most difficult defects to detect are the slag inclusions and the cracks. Why? The cracks because they have very different shapes, and for to have a model that would be accurate in detecting it, we would have a very extensive database. So, and we had a limited number of images to work on it, and this was very difficult. And the slag inclusions, they are also very difficult because normally they are inside the beads, so we would have to have some techniques to see inside it. And yeah, did I answer everything you asked, or is something?
Yes, yes, that
Okay.
was really, really clear from my side. There's a question here from Alexandra, who was asking how complex would the transfer of these models or results to laser beam welding?
Okay. How complex would be the transfer of these models results to laser beam welding? In reality, they are very adaptable. We could use these models, but we would have to use the data of the laser beam welding to adapt them. But I can tell you that this is possible to do, is not something complicated. And what would be critical changes on data between the different manufacturing methods? Okay, so in this case, yeah, it would depend on the sensors we have available to provide the data. In principle, we could use the electrical signals in the same way, and also the image cameras also we could use in the same way. Yeah, in reality, I don't think critical changes would arise here. Maybe some adaptability because of the machine, because it's not a machine, so we would have a different outcomes from the machine.
Okay, thank you, Christian. There's someone else writing a question in the chat, so we'll wait for them to write it down.
Yeah, as I mentioned, the most critical thing in this kind of work is the data, the amount and also the quality. If the data is badly acquired with too much noise, for example, then the models they will not work as they should because of this noise, for example, in the data. It would make wrong predictions, and yeah, everything starts with the data.
Okay, I have another question, Christian. Um, have you tried this solution on site with the operators of the machinery? Because the question goes because sometimes there are many operators that find these new technologies and this kind of uh, artificial intelligence and all these systems, they feel some sort of rejection to them. So have you seen or have you noted some difficulties when getting this system to the operators at the shop floor, or the acceptance was easier?
Okay, let's say it depends. There are people who accept it easily, but there are more conservative persons that sees this as a black box and don't understand how it works. And also there are people afraid that this technology would take their jobs. And in this case, this kind of people can make more difficult the implementation. But we have both kind of people in this field. So it really depends where you are going. So
Okay. I understand. Thank you. Thank you very much. So, and we have a question from Venkata. I don't know if I said that correctly. I hope I did. Which mentioned in submerged welding, how complex the system can be used in different welding speeds.
okay, how complex this system can be used in different welding speeds. Okay, when you mean welding speed, you mean the travel of the head over the the sample, the bevel, or the speed of the electrode? Okay, all right. Then, so in this case, we would have to make some trials with different speeds to enrich the data that we can provide to the model. And then we would have to check how it behaves. But in principle, it should be okay. But we would have to make some trials at different speeds. But for the electrical signals, I think this wouldn't be a problem. The implementation could be straightforward as well. Yeah, that's right. So if we are changing just the speed of the traverse speed of the system, yeah, I don't think it would be complex to adapt. Yeah. It would be more difficult if we make it with the electrodes, but with the traverse speed, no.
Okay, thank you, Christian. I think that was all, at least from my side, and it seems like there's no more questions from the audience. So what's left is just to thank you kindly for your webinar and congratulate you for it. It was really insightful and very interesting. And finally, only I would like to place the audience for next month, in May the 22nd. We'll have our next webinar from the Zero Defect Zero Web series. So we will be publishing it in our social media. And also, before I forgot, if there is any other question that arises for Christian, you can also get in contact with him through the links you can see there, either I think via email would be the easiest way, right, Christian?
Yes, that's right.
Okay, so with anything else, again, thank you very much, Christian. Also, AIMEN for the webinar, and see you around next time. Stay tuned for the updates.
Thank you very much. Yeah. Bye bye.
Goodbye.